Hi everyone, welcome to our next lecture in the Go Fly Masters series. It's my pleasure to welcome you this afternoon. As you all know, Boeing is our grand sponsor of the Go Fly Prize, and we are joined by corporate sponsor Pratt & Whitney, as well as 20 other aerospace and STEM organizations around the world. It's my pleasure today to introduce Bob Parks for this master lecture on ducted fans for hover and cruise. Bob is currently a technical fellow at Aurora Flight Sciences, a subsidiary of Boeing. He mainly works on the design of non-traditional aircraft, including subscale and full-scale prototyping. He has been working on VTOL aircraft professionally for 20 years, but has also worked on Mars aircraft, solar aircraft, submersible aircraft, and even a few conventional aircraft. Prior to this present job, he was a senior engineer at Z.Aero, now called Kitty Hawk and Cora, working on manned electric VTOL aircraft. Prior to that, he was chief aircraft designer for Aurora Flight Sciences. He has also worked as a designer on the Lockheed F-117 and as a consultant. He was a principal designer on the MIT Chrysalis, Light Eagle, and Daedalus human-powered aircraft. He first became interested in ducted fan propulsion for model aircraft over 50 years ago. His first attempt was remarkably unsuccessful. Things have gotten a lot better since then. Bob has a bachelor's degree in aeronautical engineering from MIT and a master's degree also in aeronautical engineering from Stanford. He currently holds 21 patents and is a veteran of the US Coast Guard and an associate fellow in the AIAA. So it's my pleasure once again to introduce Bob Parks.
Okay, let me get the sharing going here. Okay, what I want to talk about today is ducted fan propulsion. And one of the interesting things about ducted fans is you can use them for both hovering and doing cruise propulsion. So let's get started on this. So what is a ducted fan? Basically, you're taking a propeller and you're putting in a tube or a duct. But the design that you need to do to make this work well is very different from what you do in a normal propeller. The ducted fan, aside from the rotor itself, you've got stators, you've got an inlet, you've got a nozzle. All of these things have a strong effect on the performance, and we'll talk about that as we go along. But I think a key feature here is the duct is not too small. On the left here, you see a sort of typical ducted fan. You'll see a lot of pictures of this particular device as we go along. But on the right is what I'll call a shrouded prop, where it's a very small shroud put around the propeller. Some people do this as an attempt to improve the safety so that you can't directly walk into a spinning tip of a propeller or something. Some of them attempting to improve the performance. The problem with this is, in the cases I've seen on this, usually the result is a loss of performance compared to having the open propeller. What really makes the ducted fan work, as we will see, is the combination of the inlet, the nozzle, and the stators. And we've just left all of those off on the shrouded prop. So that's not saying you cannot make one of these work. It's just that you have to be very careful how you do it, or basically the shroud actually interferes with the propeller. So continuing on, ducted fans have been around for quite a while. And here is some example of prior art. A fair number of these things have actually flown. Starting on the left side of the screen, that column, those are all of particular interest to me because those were all Aurora Flight Sciences airplanes, and I was involved in some level of each of them. The one at the top was called Excalibur. The thing in the middle is a tilting turbofan engine, but then it was actually an electric turbine hybrid, which used 3 ducted fans that you can see. And they added to the hover thrust and also gave attitude control in hover, counteracting some of the slow throttle response problem of the turbine engine. That did hover successfully. The thing I'll point out on this is, while we've got it on the screen, is that the fans in the wing, once they shut off, they actually retracted into the wing. This was a high-speed, low-altitude airplane. It didn't need a whole lot of wing on it. So the fans would just slide in. It was basically very fancy drawer slides. And that's actually a very good way to cover up what's otherwise a very draggy fan in cruise. The one underneath that, it was a GoldenEye 50. This was a series of ducted fan tail sitter airplanes that were done basically about 15 years ago. Single ducted fan, stators took out the torque, variable vanes in the back gave you control. The one at the bottom is the Aurora Lightning Strike airplane. This flew as a subscale, but there were problems with the hybrid power system that resulted in not finishing the full scale. And it's a bunch of ducted fans, 24 of them in this case, and they're actually very tightly integrated with the wing and the canard. So this was an extremely challenging design problem. You can make something like this work, but there was untold amounts of CFD and test time that went into getting all the shapes and the design of this thing working. Crossing over into the center at the top row, that's a fenestron. It's used as a tail rotor on some helicopters. Potential safety advantages, the noise signature is different. So you could argue that it's not quite as objectionable as the tail rotor on a normal helicopter. The other one at the top is the X-22A VTOL. This was done in the early 60s. 4 turboshaft engines, a lot of shafts running all over the airplane, and 4 big tilt fans. So this was a successful airplane. It flew pretty well, although it was kind of dragging and it couldn't go that fast. Down underneath that is, oh geez, I forgot what the name of this was. It's basically a twin ducted fan personal air vehicle. The very, very close to what the goals in GoFly are. You know, it does probably meet the size constraints. And it's one approach to doing this problem. I don't know the exact performance specifications on it, but it's predominantly a hovering vehicle. Going over into the middle, that is the Boeing Phantom Swift. It was a competing proposal against the Aurora Lightning Strike, high-speed tilt ducted fan vehicle. Both of those vehicles were supposed to do 350 knot kind of speeds. And so it tilted the outer 2 fans, and there was 2 fans embedded in the fuselage. And then finally at the bottom is the XFV-5A. That's 3 ducted fans, very high disc loading. It was an attempt to make a vertical takeoff and landing fighter. And what this actually did was it tapped off all of the exhaust flow from 2 jet engines, ducted it through the airplane, and drove the fans with tip turbines. So the airplane had some issues, but it did fly. Okay, first thing you want to consider about all of this is what's called disc loading. And that is, you've got a rotor of some type. It has a reference area or disc area associated with it. And how many pounds or newtons of thrust do you get per unit of disc area? And on one side, all the way off at the right here, you have things like the X-35 or F-35B, the Harrier, vectored thrust turbine engines, or very high disc loading fans, and very, very high disc loadings and very, very high power requirements. In the middle, you've got lift fan type aircraft, somewhat lower disc loading, but the power levels are coming down. And then you progress through tilt wings, tilt rotors, and all the way to helicopters. And helicopters are very light disc loading, sometimes as little as 2 pounds per square foot. And as a result, you can have something like 15 horsepower of thrust per pound. Now, given the size constraints on GoFly, I'm going to guess that these things would want to be somewhere in the 20 to 50 pound per square foot disc loading region, sort of where that cloud is. Okay, so ducted fan advantages. So both the fan and the open propeller have advantages and disadvantages. The first advantage for the ducted fan is it can be smaller diameter. I'm not going to really get into it too much here, but the physics involved says that the exit area of the ducted fan is what matters. It's not the rotor area, it's the exit area. And that can be half of the disk area of the equivalent propeller. Now, that's the very simple physics argument. In reality, it's not quite a half. But so basically, you can be down at the square root of 2 on the diameter. And that's certainly an advantage when you're size constrained. The fact that you're smaller diameter on the rotor means it can also run at higher RPM while keeping the same kind of tip speed. The noise is mostly a function of tip speed. So if you can spin faster, that means for a given amount of power, that means the motor torque is lower. And in a lot of cases, the weight of the motor or engine is driven by the torque and not the power. So maybe you can get some weight advantage. Next thing is we'll go into this a little bit on the next few slides. But if you have a duct or a propeller and you're using it to make hover lift, and then you tilt it for propulsion and forward flight, the ducted fans hold their thrust much better with increasing speed than an open rotor will. Now, you can always make either one of these variable pitch. That helps a lot, but it's also a lot of complexity for what you would hope would be a small, simple flight vehicle here. The ducted fan might be less noise. There's certain noise terms that it very much suppresses compared to an open rotor. The problem is it adds in some of its own unique noise sources. And then finally, the ducted fan is somewhat safer. You know, the prop is shielded. You're not going to step into the tip of a spinning propeller. The issue is, if you looked at the downwash speeds on the previous slides, these things are still producing wind speeds about the level of a hurricane. So they're sucking in a lot of air, and you have to be careful. You get close to it and things will get sucked into it. So it's a safety advantage, but it's not, you know, saying that now we're ultimately safe. So disadvantages. Well, you've got a duct, and that duct has weight. You've got to build it. It has to be reasonably stiff so you can get the precision you need. So that adds some weight. And it adds wetted area. So the more surface area you have, the more skin friction drag you have when you're trying to go in forward flight. And so even if you tilt it, that's a lot of drag. If you have a ducted fan and you don't tilt the duct, then you really need to cover it up or retract it or do something to cover up this big hole. That's particularly true if you're putting the duct in the middle of a wing, where you've potentially got flow through the wing that's messing up your wing lift. So you've got to deal with tilting it, covering it, doing something. So that's always going to be a little bit more complexity. And you need to have all the parts be pretty precisely made and pretty stiff. One of the keys to making a ducted fan work well is you need a small gap between the tip of the rotor and the duct. And, you know, usually you're trying to talk about things that are, you know, on the order of like 1% of the radius of the rotor. So a pretty small gap, you know, we're talking, you know, 1/10 of an inch, few millimeters kind of thing here. So that means that the duct has to be round. You've got to mount the fan in the center of it. It has to be stiff enough that if the fan is shaking a little bit, and it always is going to shake some, you don't run the tips into the shroud. So you've got to work on that. And then the final thing, all of these extra features that we're adding to the ducted fan compared to the open rotor are giving us the advantages, but you also have to design them properly to actually make everything work. And there's a lot of ways to mess things up that you just don't have with an open rotor. So anyway, for the size comparison, what I did here is I said, okay, we've got a GoFly vehicle. It's a 200-pound, 91-kilogram payload. And, you know, going off of some of the previous lectures, it came out that, oh yeah, if you're lucky, you'll get a payload to be about a third of the total gross weight. So what I did is I said, okay, we're going to do a quad ducted fan. Think of something like the V22. The V22 worked pretty well. And we're going to put 170 pounds or 750 newtons of thrust on each fan. And then I said, okay, about 30 pounds per square foot off of the disk loading chart. And I designed the fan that's shown in the front and oblique views here. And it came out that it wanted about 23 kilowatts or 31 horsepower to make that much thrust. So comparing the size, the fan nozzle exit diameter is 21 inches. Oh, incidentally, I didn't actually try packing these into your 8.5 foot maximum dimension. But anyway, the fan is 21 inches exit diameter. That's the critical thing for figuring the performance. As it turns out, that gave about a 22-inch, 560 millimeter diameter fan. And the outside of the duct was about 700 millimeters or 27.5 inches. And I looked at a few of these, but the one that looks pretty reasonable spun at 6,000 RPM. So then I went and I designed a hovering propeller. And I basically just scaled the diameter while holding the thrust constant until I matched the 23 kilowatt power level. And that came out with a 33-inch diameter. Now, that's a 1.5 factor on the fan diameter. It's not quite your normal square root of 2, but these fans have the duct losses. They have a hub in the middle, all of those things that are not in the zeroth order physics model. But these are two equivalent ones. So, yes, the fan is a bit smaller and it is a bit safer, but it's not dramatically smaller. Anybody who's saying, oh yeah, we can do this fan, and to do this it could be, a quarter of a meter or 10 inches in diameter. Well, yeah, you can do that, but it's going to take a whole lot more than 23 kilowatts each to power it because of the higher disk loading. So one of the things I said is the fans can let you go faster. So we're talking a V22 type tilt fan. So taking these fans and then changing the forward speed and just look at what the performance is. Now, a big factor in this, in reality, is what are the characteristics of your engine? Different engines, piston engines have different torque versus RPM behavior than electric motors do. And so you've really got to go do this keeping in mind the performance of your power system. But a really simple thing is I said, I'm just going to hold constant RPM on the rotor and then look at what happens with airspeed. So one of the things that happens is the thrust falls off very rapidly with airspeed. The net output power of this propulsion system is the thrust times the airspeed. And so you've got constant RPM, no more than constant power. You go faster, the thrust has to go down. But if you look at these two curves on the left, going out to 60 meters a second, that's 120 knots. That's probably faster than most of the GoFly vehicles are going to go. The ducted fan is still holding in at over 200 newtons of thrust, about 30% of what the hover thrust was, whereas the open propeller went past zero thrust before it even got to 50 meters a second. Again, if you made the rotor variable pitch, you could change this and improve the propeller, but this is an inherent advantage in the fan. Now, if you look at the power absorbed, as the rotor goes faster, it's basically unloading and it can absorb less power at the fixed RPM. But the fan keeps the power levels up a lot higher for a lot longer. But basically, for the open prop, beyond 50 meters per second, what you really have is a windmill. and the power is going the other way. So what does the ducted fan really look like? And I showed this image before. So we've got about a 30 pound per square foot fan. And one of the characteristics of this is the flow is fully subsonic. If you want to get more technical about it, it means you consider the air to be an incompressible fluid. And your design tends to be sort of like this. You don't have an awful lot of blades. The solidity, which is basically the blade area to the disc area ratio, is pretty low. There's no overlap on the blades. And you end up with something that looks roughly like this. On the right side here, we've got a CAD image of a modern airliner turbofan. And these things at static thrust for takeoff are somewhere around 900 pounds per square foot. So 30 times higher. The other characteristic on these is they usually involve some amount of supersonic flow. To make the tips of the fan work, they end up usually being somewhat supersonic. Now, I don't know the specs for this particular fan, but this very fancy, curvy, sweepy blade shape, a lot of that is probably there to make the fan work better in supersonic and transonic flow. And some of the shape is to balance off the sweep effects that they're doing at the tip, that you're sweeping the tip to make it work better at high Mach numbers, and then that would cause a structural load in the blade when it's spinning. So the shape inboard is just coming up with something that sort of balances out the structural loads. Now, like I said, I'm not an authority on how to design these devices, but that's what it looks like to me. Anyway, if you come up with a fan that looks like this airliner fan, but your goal is to make a 30 pound per square foot VTOL fan, you're probably doing it wrong. So getting into the rotor design. All of these designs are done with an analytical tool that's quite appropriately called Ducted Fan Design Code. I'll give more information on this at the end. But it's a really good tool for designing these low Mach number, low disk loading hovering fans. It was originally developed about a decade ago, a little bit over, by the Defense Advanced Project Research Agency, or DARPA, to aid the development of those tail-sitter ducted fans that look like they might have military use at the time. Anyway, so all of these were designed with that code, and it's a pretty reasonable way to get a quick design of a ducted fan that's pretty good. It's not perfect, it doesn't cover everything, but it's a really good way to get the basics right, or to show you that, yeah, you're really doing something wrong. So you can pick a wide range of RPM for the rotor, and they all work the same. I was originally going to give performance curves of these 3 rotors, but when I went to plot it, all the lines were on top of each other, and you couldn't even tell that there were 3 lines there. So you can go to a lower RPM, and what happens, you end up with more blade area, and the pitch increases. This is a front view of the fan, and the blades look like they really neck down to a small chord here, but what's happening is that they're growing dramatically in the axial direction. So the root chord on the 4,500 RPM is actually quite large. Anyway, as we go to higher RPMs, you need less blade area, less solidity, and you just tend to cut down on the number of blades, or you end up with these very high aspect ratio toothpicks that are not very good for structure. So all 3 of these fans would be buildable. They'll all work. The lower RPM fan needs more torque to have the same power. That means the motor is going to be heavier. But the other thing is the lower RPM means less noise. And the predominant noise features or production on these fans is a very strong function of the tip speed or tip Mach number. And in some cases, it's like the 6th exponent. So the difference between the 4,500 RPM fan and the 7,500 fan could be something like 20 dB here. Now, there's a lot of other factors going on. But saying that it's well over 10 dB potentially is certainly true. Okay, the stator design. Once you've got the rotor, you have to design the stator. And the first thing you've got to do in the stator, well, it's mainly there to support the center body. You've got to have something to hold the motor and the fan hub in place. There's some work done on hubless fans. There's some potential advantages there, but it's horrendously complex. Right now, it's very heavy, and you don't have the time to go develop something like that. But so you've got to have a center body. You have to have supports for the center body. That means you have to have some struts. The struts might as well be stators. And then the goal is to minimize the drag of those stators. Now, the fan flow has some swirl in it. That's inherent with any propeller or fan. And the amount of swirl is really a function of what the torque is. Action and reaction. The motor is putting torque in, and that's all reacted out by the swirl and the exhaust flow. So we might as well try to take that swirl and straighten out the flow, and that turns into more, axial flow speed out the back and more thrust. So the thing is, for these 30 PSF fans, even at the 4,500 RPM case, there's just not a lot of swirl there. The pitch angles are not too high. The 4,500 at the hub was getting pretty steep pitch. But if you didn't require the swirl, it's not a huge loss in the performance. We're talking 5, 10, 15% kind of numbers here. But since you have to have stators anyway, you might as well make them work and get the swirl out. And if nothing else, you're counteracting some of the drag that the stators would have otherwise. Now, when you design these, you can exactly cancel the motor torque at one operating condition. As the airspeed changes, as the throttle changes, you're not going to have a perfect compensation. But in practice, you can get about a 90% compensation over a reasonable operating range. So in terms of what you need for recovering the swirl energy, 90% is pretty good. If you've got a single fan and you've got to do anti-torque, no, it's not good enough. That's probably going to need some sort of variable vanes to control that. Now, the stators can either be ahead of or behind the rotor. And if you saw the noise presentation that was done in the Masters Series lectures a while ago, the three guys from NASA Langley, they talked a lot about unsteady flow noise sources. So anytime you have two sets of blades in proximity to each other with one of them moving relative to the other, they're producing unsteady, the one upstream is producing unsteady flow on the one downstream. There's a little bit of an effect going the other way, but that's much weaker. So what matters, though, is the speed of the object encountering that unsteady flow. So it's actually quite a bit noisier to have the stators upstream than it is to have them downstream. That's why your typical fans put the stators downstream. So anyway, looking at the designs on the right, these were all done for the 6,000 RPM baseline fan design that I did. And this is partway out on the blade. So you see a cross section, the rotor blade that's passing by is on the left. The arrow indicates the direction that the airflow is coming off of the stator or coming off of the rotor. And so you want to design a stator that works with the flow coming in at that angle. So since this is not a lot of swirl, we can take a pretty normal conventional airfoil and, that airfoil works at that angle of attack. And as the inflow angle changes, as your operating conditions changes, it will work over a wide range. And this is a pretty nice, robust solution. If we went into something that had a lot more swirl, we can start doing stators where there's more camber up at the front. and you sort of hook the front of the stator and align it with the flow, whereas the back of the stator is pretty much axial down aligned with the duct. You actually make your stators so that they slightly over de-swirl the flow where the stators are, because they're not as effective halfway between two stators. It doesn't get as unswirled quite as much. So what you're trying to do here is get the average flow coming out the back to be unswirled. Anyway, as you go into more swirl, you start hooking the leading edge a little bit. But then what you want to avoid is a situation like on the bottom. And you see this on a lot of fan designs. Somebody's saying, oh yeah, we've got huge swirl on these things. And sometimes they will hook the stators so much that they've got almost a 90-degree curve in them. And the leading edge of the stator is aimed almost in the plane of rotation. And no, the flow doesn't like doing this. It's going to be basically separated on the bottom. It's a lot of drag. Occasionally you'll see a ducted fan write-up that says, oh yeah, we fixed the stators and we got huge performance improvement. That's usually because they had done something like this before and it was bad. So anyway, the goal here is don't do anything bad. So we talked about the speed range, and I showed those curves of the thrust versus speed. And this is just some streamline plots of the baseline fan design at 4 different airspeeds: hover, 10, 30, and 60 meters per second. So that's 20 knots, 30 knots, or 20 knots, 60 knots, and 120 knots. And you can see that the way that the flow goes. In hover, the flow is really hitting the outer wall of the duct about halfway back, going forward, going around the inlet lip, and then through the fan and out. And as the speed increases, that stagnation point starts shifting forward. And if you look at the 60 meter per second case, the capture area, which is the disk area of the flow that's actually going to go through the fan, is actually a little bit smaller than the lip diameter of the fan. But with this kind of shape on the outer wall of the duct, it basically works over this entire speed range. And so if you want to do a tilt duct, this is the general kind of shape that you want to have on the outer walls. So you need a pretty good radius on the inlet lip so that in the hover case, the flow can go around it. If that was a sharp leading edge, you would literally lose half of your hover thrust. All of the duct thrust effect would go away. But anyway, this is a pretty good, very robust kind of design. You can, if it looks like this, it's probably going to work pretty well. So other examples here, well, on the left is just a cutaway view of the baseline here. And a feature of this is basically downstream of the rotor, the flow cross-section area stays constant all the way to the exit. So as the center body tapers away, the outside of the duct has to come in a little bit. And anyway, the exit diameter is marked. And when you're figuring the disk loading, it's this exit diameter that matters. You can make the rotor diameter anything you want, and as long as the flow stays attached going through the duct, then it doesn't matter what the fan is, only the exit diameter matters. Now, of course, that brings up the obvious question, well, why don't we enlarge the exit area? And so that's what we have on the right here. So that's a diverging duct, sometimes called a diffusing duct. And so the area is increasing significantly. The issue is if you do this too much, the flow separates. That's the same as what happens on a wing stall. And it doesn't go out and it doesn't fill the whole nozzle area. And your performance takes a big hit. The risk here is that if you have, say you're hovering and you have some crosswind or you're transitioning to forward flight and you have an upstream disturbance, that can trigger the downstream flow to separate, and all of a sudden you just instantaneously lost a lot of thrust. So yes, you can do this. I think the X-22 had about a 15% diffusion. I don't know if that was on the radius or on the area, but they did that. So you can do these kind of things. You just have to be very, very careful when you're doing it. And predicting when it's going to happen is actually a pretty challenging problem. So another common duct shape you see for things that hover is sort of like what's on the left, where you've got a flared inlet. And they're saying, oh yeah, we're pulling in air over a wide angle. We'll flare the inlet out to better receive that. But in the process of doing that here, they also made it sharper. And if you recall back on that hover flow streamline diagram, the flow is actually trying to come in into the middle of the duct and then go forwards around the lip. And we've just made that a lot harder to happen. So while this might be a pretty good duct shape for, say, 20 meters per second, it's not necessarily a good one for hover. If you only care about hover, then you can do a bell mouth like the one on the right, and you see these very commonly for ground testing jet engines and things. But this will let the flow attach over a wide range. You've got this big broad surface, so your low pressures give you a significant forward thrust, and it will work. It's just that if you want to tilt this and use it for cruise, then it's pretty draggy. So that brings up the question of ducts and crossflow. And this could be a case of you've got a hovering vehicle and you've got a crosswind. It could be a case of you've got fixed ducted fans and you're trying to transition. It could be a tilt ducted fan where you're not tilting it to align with the incoming flow. But normally in a pure hover like we have on the left, the flow is coming in pretty symmetrically and it all works pretty well. But when the flow is coming in from the side, the flow coming in from the left here has a momentum. There's a mass flow, there's an airspeed, and then basically the horizontal component of that flow has to go away as the flow turns to go vertically through the duct. So you're taking that momentum and reducing it to zero, and that produces a drag force, which is called the momentum drag. And it's just the mass flow rate in slugs or kilograms per second times the velocity. And you go through all the unit conversions, so that turns out to be a force in pounds or newtons. And it can be pretty large. The mechanism for making that flow turn is basically you have a lot of suction here on the upwind lip of the fan. And that also gives you a moment where it tries to make the whole airplane pitch and rotate so the top goes to the right. And that's something you have to counteract in your transition by whatever control methods you have. The other risk is you've got this high suction here. If that corner is too sharp, the flow separates, and then your fan gets very unhappy and a lot of thrust goes away, and it probably gets pretty noisy in the process and shakes a lot. So this is something that you have to be very careful of. Okay, finally, noise. If you go back to the noise lecture that I mentioned, one of the terms they talked about was the thickness noise, which is just you've got this rotating blade. The blade has thickness. It's causing air to move out of the way as it goes by. And that particular type of noise can get blocked pretty effectively by the duct. It can also, since it's getting rid of the tip vortex on an open-tipped rotor, it can also get rid of a lot of that noise. But the big issue here is you've got the rotor-stator interactions, and that's an unsteady flow noise. The primary frequency of this is at the blade crossing frequency. So basically, anytime you have a rotor blade pass a stator blade, you get a pressure pulse. And the more of those, well, you have to go work it out exactly how that happens for your the number of rotor blades and stator blades you have. Normally, you want to have different number of rotors and stators, because if you had 5 rotors, 5 stators, they all hit this at the same time, and you get a pretty big pressure pulse and also a little bit of vibration out of it. So to run smoothly, you want to mismatch the number of rotor blades and stator blades, like no common denominators. So 5 and 7 are both prime numbers. That works pretty well. But in the case of this baseline fan, you've got 35 pulses per revolution, 6,000 RPM. That comes out 3,500 hertz for the blade crossing frequency. And if you look at the dBA weighting scale, that's right where the human ear is really sensitive and very, the noise is a very big issue at that frequency. So this is a problem. An issue is it's also very, very difficult to predict it. There's some simple methods where you can predict the noise of an open propeller, at least as long as it's fully subsonic. That's a pretty easy thing to do. There's programs that do that very easily. The accuracy varies according to how much work you want to put into it. But when you get into these interaction noises in a ducted fan and you get into acoustic modes in the duct, this is all a very, very messy problem. And this is a serious professional grade problem. You throw a few experts and a whole lot of computer time at it and wait a long time to get a result. Now, since you do have a fan in a duct, there are cases where you can add acoustic absorbing to the inside of the duct, and that can make a difference. The key here is you want to match up the frequency response of the absorber with the frequencies that the fan is putting out. One of the GoldenEye series airplanes that I showed one of it back at the beginning had a noise requirement. It was a 140-pound airplane. The requirement was hover 500 feet over somebody's head without them being able to hear it. And we were able to meet that requirement. So since the big issue here is the rotor-stator noise, how do we reduce that? Well, you can do a little bit of it by picking RPM and blade count to put the frequencies where you want. Having more blades also generally is better than fewer blades, even though the frequency is going up. Again, you've sort of got to do a case-by-case basis. This isn't a good thing for a compact vehicle like a GoFly, but if you can keep the rotor and stator very far apart, the issue is you've got a sharply defined wake coming off the back of a blade. When that hits a stator blade, you get your pressure pulse. Well, if you move the rotor well away from the stator, then that wake deficit has a chance to sort of blend out, and then it doesn't make as much noise. And this is particularly true at the blade tips. You have the highest airspeeds going on there. So for instance, if in the side view you sweep your stators so they're further away from the tips of the blades than they are at the hub, that can help by a few dB sometimes. And that's actually still a pretty good structural configuration in most cases. You absolutely want to avoid multiple blade crossings at the same time, like having 6 rotor blades and 9 stator blades. They've got a common denominator of 3, so you always have groups of 3 blades crossing. That makes it worse. You can sweep the rotor blades either fore or aft, and what I pulled up here is a quiet electronic cooling fan, because this picture shows these features pretty well. In this case, the fan is spinning counterclockwise, so those rotor blades are swept forward. For a low mass, low speed device like this, you can get away with the forward sweep. With higher speeds, it could be a structural problem. But you have the sweep forward on the blades. You can also do sweep aft. What that does is it means you're not having the pressure pulse all happen at the same time. It sort of smears out the pressure pulses. And then non-radial stator blades, in this case, they're actually curved. So not only do they not go into the axis of the rotor, but they go in off to they're offset to the side, but they're curved. So that basically when you look at the wake of that rotor blade, how it interacts with the stator, there's only a very small interaction region at any given time. So instead of a sharp pressure spike, you get a much lower amplitude, much broader one. So you cut down the harmonic content and you cut down the peak of the noise. So that all works pretty well. So anyway, finally, resources. A couple of useful books. Both of these talk somewhat about the momentum theory of rotors, which also includes how you deal with fans. There's also some pretty good stuff in Wikipedia. Most of the stuff I've seen there has actually been pretty accurate. I think the Johnson book I looked at, one of these was really expensive when I looked it up last night. It was about $100+, whereas the other one you could get a PDF or you could get a Kindle version of it for $20 or a used paperback for less than $20. I think it was the Principles of Helicopter Aerodynamics was a little bit cheaper. For the software, like I mentioned, all of this was done with the Ducted Fan Design Code, commonly called DFDC. It was written for DARPA by Professor Mark Drala and Harold Youngren. They've done a bunch of other useful aero codes like X-Foil and AVL and X-Rotor. Anyway, here's a link to it. The project was sponsored by DARPA, and as typical for software projects, they always take longer and cost more. And so the version of DFDC that is out there is 0.7. It never made it to 1.0. There are bugs in it, but it's by far the best thing around to make a first pass at designing one of these fans. It does the fans, it does the stators. It is a challenging code to use. It's command line driven. It's basically was written in Unix and X Windows. So you're typing commands at it. And the graphics are, pretty primitive line graphics. You're not going to get 3D renderings out of this. So you're going to have to spend some time learning how to use it. And it was written by engineers for engineers. So expect to put some time into it. Now, that version is 0.7. A guy in Canada, Philip Carter, his company is Isotech, liked the code and did some work on it, and it made some improvements on it and also got rid of some of the bugs. And so this is the version that I normally use, and the link is there. So one of the things that it does that's pretty nice is it corrects for the blade volume. That's an issue on the fans. The blades take up volume in the ducts, so the flow speed going by the fan is a little bit faster than it would be if you didn't allow for the volume. So this is a more complicated level on the design, but it does it. And then finally, Philip started up a Yahoo discussion group on DFDC, and the link is here. And I usually read that every time it happens. It's a very low traffic group. It will go for a month, sometimes with no traffic. But when you start trying to use this, you will have some problems. And the people who are experienced on the group expect you to have done what you can to solve your own problem first, but then intelligent questions will usually get well thought out answers. So anyway, that is all of it. And I guess it's time for questions.
Thank you so much, Bob. That was incredibly informative, a lot of information that we've now shared. I want to remind everyone to use the QA button on your Zoom webinar, as well as the chat function, to be able to send any questions over to us. We have one question for you is, how should we think about inlet shapes when the fan is embedded in a broad surface, like a wing?
Okay, fan and wing is a really tough problem because they very strongly interact. And you also have the issue of, well, if it's in a wing, then you've got to go through transition, you've got sideways flow. There is some like technical reports like from the Ryan XV5. Anyway, it's a tough problem. Inlet lip stall, separation stall in transition is a really big problem. You can probably get a fair amount of the pressure thrust off of the top of the wing when you do something like that. DFDC doesn't really cover cases like that. I sort of make a giant flat slab donut and put a duct in the middle of it as an analysis case. And it seems to be pretty happy with that, but I'm not sure how valid the answer really is. So yes, you've got a significant problem there, but the fact that you're putting the fan in the wing means you're trying to make a transition. And the interaction of the fan flow and the wing flow is a really messy problem. I happen to like doing actuator disc type CFD as a first pass analysis on that. That will at least show you somewhat of what the fan to wing interaction is. I think Dan Newman pointed it out, where you put the fan in the wing makes a big difference. If it's in the trailing edge, it's enhancing the wing lift. If it's in the leading edge, it's fighting the wing lift. So it's a tough problem and expect to put a fair amount of work into solving it. I hope that was a good enough answer. Sorry, I can't say, oh yeah, do it this way.
Do you have any comments on contra-rotating propulsors versus stators?
Yeah, actually something like DFDC can deal with a counter-rotating fan. You basically, a stator is just a fan with 0 RPM. So it will cover that case. Obviously, the mechanical complexity is worse. You may not get that much better torque compensation than you do with a stator. It's still going to vary according to what's going on with the flow conditions. One thing that is going to be worse is the noise. Anytime, you've now got a weight coming off of a high-speed rotor encountering another high-speed rotor. So this is the stators in front problem, only even worse. So that is an issue. If you're doing open rotors, Philip Carter did a enhancement on the X-rotor open propeller design code that actually better handles counter-rotating rotors. I don't think it's really been validated, but a key thing on counter-rotating is it's going to be loud. And you've got a noise requirement here. So given that and the complexity, I would really try to stay away from it. Stators will do pretty much as good a job, simpler, lighter, and quieter.
Okay.
Incidentally, if you had a case where your solidity on the fan was already up, looking like an airliner turbofan engine, and you still could not absorb all the power you needed to fit into that little rotor, then multi-stage with stators in between it or counter-rotating are ways to solve that problem. But those are disc loadings that are so far above anything I think you would ever want to use for GoFly. It's just not worth it. Okay, next one.
What pitch propeller do you recommend in a bell-shaped intake duct 3-bladed prop?
You have to really go work that out. It depends entirely on how much thrust you're trying to get. It's the thrust and the RPM. A quick look at it is if you do the basic momentum equations. If you go look at actuator disc or disc loading on Wikipedia, they will give you all the information. It's pretty simple equations. but you've got a disc loading that turns into what the flow is out the back of the duct. If you say the duct is roughly constant cross-section flow area, and then you've got some RPM, and if it turns out that the flow is moving 6 inches for every revolution of the rotor, then I would start out somewhere around a 6-inch pitch. It might want to be 7-inch. Propellers still make thrust going faster than the so-called pitch speed. Anyway, I would start out doing it that way, but it depends on what the disc loading is.
Okay. Does larger outlet diameter generate more thrust than smaller outlet diameter, assuming no flow stall?
Basically, if you're holding the power the same, the answer is yes. The question is, how far can you push the diffusing duct before it does stall? So the relevant thing for the disc loading here is the duct exit area. And go back to that really early chart showing the disc loading effects and the power loading, which is horsepower per pound or pounds per horsepower, whichever way you want to look at it. The lighter the disc loading, the more pounds of thrust per horsepower. So yes, if you can get a larger exit area and have it work, then that's better.
Okay, next question. Is it helpful to have adjustable blade pitch inside a ducted fan? If so, how do you do that?
Okay, the mechanisms are very similar to what you would do for a variable pitch open propeller. And there's a lot of ways that has been done. There's what you find on airliners and World War II fighters, where it was generally hydraulically actuated, but there's electric systems, all sorts of different ways of doing it. You can even do things sort of similar to what you do with a helicopter swash plate, although those give you cyclic pitch, which you don't need here. You can do all of those things. For example, the Lightning Strike vehicle that I showed the image of at the beginning, that actually had variable pitch fans because it had to go from hover to 350 knots. And that's just too wide a range. The other thing that's interesting on a ducted fan that you can do, we talked about the advantages for getting more static thrust by making the exit area larger. Well, you can go the other way too and make the exit area smaller. And what that does, if you saw that plot I had of power absorbed versus airspeed, basically the faster the air is going through the duct due to the flight speed, the less angle of attack the blades have, so they offload and they can't absorb as much power. Well, if you constrict the exhaust with a smaller exit area, then you're basically changing the flow speed at the fan relative to the flow speed at the outlet. And that has an effect very similar to variable pitch. You can't make it work over as wide a range, but you can make it work over a pretty wide range, and making a variable nozzle, with a flap or something is certainly a lot easier to build than variable pitch. So that is worth looking at. I will point out that if you're talking a high-speed flight case, there seems to be an issue in DFDC where it doesn't handle these constricting nozzles very well. And maybe that will get fixed sometime soon. But I've heard that for the last year and a half.
Okay, we'll take 2 last questions. Comments on prop location for induced lift at leading edge versus trailing edge?
Dan Newman covered that pretty well in his presentation. I would say go look at that. But if you get back to the basic circulation theory of lift, where you've got sort of a big vortex in the middle of the wing, and it's making the flow over the top go faster and the flow under the bottom go slower. And then with that difference in speed and Bernoulli, you get the pressure difference that gives you your lift. Basically, if you put the fan near the trailing edge, it's accelerating flow over the top front of the wing, and that's helping your lift, and it's blowing down at the trailing edge, which is sort of working like a jet flap. Whereas if you put the fan at the leading edge, it's trying to pull in air in from the trailing edge over the top of the wing, which is cutting the flow speed over the top. And then you're basically dumping this flow out over the bottom, or out the bottom, and messing up the lower surface flow, which is cutting the high pressure there. So anyway, Dan covered it pretty well, so I would suggest looking at that.
Okay, great. And our last question, Bob, are there other public tools you could point us to for preliminary rotor design and power design?
Okay, for open rotor, X-Rotor, it's an MIT program. It's just like it sounds, X-R-O-T-O-R. And it does open rotors if you can use DFDC, you can use X-Rotor. It's written by the same people with the same kind of command structure. X-Rotor is actually quite a bit easier to use. So that covers the open rotor case. I don't really offhand know about other good ducted fan tools. I know there's some out there, but this is sort of an issue where if you don't model enough of the phenomena, then you're not necessarily going to get a very good result. If you do go get DFDC, there's a theory of how this was done documented in there. And, hey, I got a couple degrees in aeroengineering, and I struggle with that one. It's complex. So the simple answers probably have a big risk of not being accurate enough.
Okay, that's all of the questions we have today, Bob. Thank you so much for an incredibly informative and knowledgeable master lecture. As always, we will be posting this to our YouTube channel so that you can reference it after this webinar. Thanks so much, Bob.
One final comment. I did post that Yahoo group for DFDC. Like I say, I read that pretty regularly. If somebody posts a question there, I should get it within a day or two.
Excellent. Thank you so much, Bob, for offering that resource.
Okay.
And if we have other questions that come in, we'll certainly keep you informed and share that with the community as well.
Okay, great.
Thanks, everyone.